This is episode 1 of Probability, a historical series. Let's start with something strange. The branch of math we call probability theory wasn't first worked out by some professor in his study, it was forced into existence by a gambler's complaint. The core question of this episode is just one sentence. A veteran gambler had a betting scheme his gut told him should win, so why did it keep losing him money in real play? The answer takes us back to Paris in 1654. In 1654 Paris there was a nobleman who loved betting on dice, nicknamed the Chevalier de Mere. He'd gambled for many years, relying on a feel for the odds he'd developed himself. But one day he noticed that a new bet his intuition said should win was actually losing him money in real play. He couldn't figure it out, so he wrote to the greatest mathematician of the time, Pascal. Was arithmetic itself broken? Pascal got hooked on the question and pulled in another great mathematician, Fermat, to discuss it by letter. Those few letters back and forth gave birth to the entire field of probability. See that a gambler's letter of complaint started a whole branch of mathematics. Let's get clear on de Mere's money-making signature bet. The rule is simple: take an ordinary six-sided die and roll it 4 times in a row. If at least one 6 shows up in those 4 rolls, he wins. If no 6 shows up at all, he loses. A die has 6 faces, each equally likely, so the chance of a 6 on one roll is 1 in 6. De Mere made a living off this bet for years, so he was dead certain: roll 4 times, get at least 1 6, a sure moneymaker. But the question is, exactly how sure? For that, we have to actually do the math. Here's a little trick used over and over throughout probability theory. To find at least 1 6 in 4 rolls, counting 1 6, 2 6s, 3, 4, gets messy fast. The smart move is to flip it around. First work out the opposite: no 6 in any of the 4 rolls. Those two cases together cover all possibilities, that is, 100%. The chance of not rolling a 6 once is 5/6, not rolling 1 4 times in a row is 5/6 multiplied by itself 4 times, that is 5/6 to the 4th power, which works out to about 48.2%. So the chance of at least 1 6 is 100% minus 48.2, about 51.8%. Remember this flip it around trick: whenever you hit at least or at most, your first move should be to compute the opposite. 51.8% doesn't look much higher than half, but in a casino that's plenty. A win chance just a hair above the loss chance means that, repeated enough times, on average you come out ahead. That's exactly why de Mere ate well off this bet for years. Notice a crucial number popping up here: 50%. It's the dividing line between a fair bet and an unfair one. Above 50 you have the edge, below 50 you're at a disadvantage. Burn this line into your memory: the very next bet is going to turn on it, and we'll see exactly where de Mere went wrong. Tired of one die, de Mere upgraded to a new bet with 2 dice. Full of confidence, he scaled the rule up proportionally. And that is where the disaster begins. The new bet went like this: roll 2 dice together and bet on getting double 6s, 2 6s at once. When you roll 2 dice, how many combinations are there in total? 6 possibilities for the first die, 6 for the second, multiplied together is 36. Of those 36, both 6s is just 1. So the chance of rolling a double 6 in one throw is 1 in 36, a lot smaller than the 1 in 6 for a single 6. Since the per throw chance shrank, he'd need more throws to make up for it. The question is, how many throws does it take to turn this new bet into a sure moneymaker too? Here's how de Mere reasoned: with one die I had 6 faces in 4 rolls made me money. The key ratio is 4 to 6. Now with 2 dice the number of cases jumped from 6 to 36, exactly 6 times bigger. So I'll scale the number of throws up 6 times too, from 4 to 24, the ratio is still 24 to 36, which reduces to the same 4 to 6. Same ratio, so the odds should be the same, right? This scale it proportionally idea sounds perfectly logical, and he believed it completely. But reality was brutal. Betting on this idea, his money slowly drained away. Where's the mistake? The mistake is this: across repeated trials, probabilities multiply, they don't add. 5/6 to the 4th power and 35 36 to the 24th power simply will not come out equal just because the base and the exponent are in proportion. Let's honestly compute it again. First the opposite: in 24 throws, not a single double 6 appears. The chance of no double six in one throw is 35/36. Not getting 1 in 24 throws in a row is 35/36 to the 24th power, which works out to about 50.9%. Notice it's over half. So the chance of at least one double six, the chance of winning, is 100% minus 50.9, only about 49.1% below the fair line. In other words, the new bet Demir thought was a sure win is actually a slow money loser. For the first time, his intuition got slapped in the face by the cold hard numbers. Put the two bets side by side and it's obvious. The first bet, win chance 51.8%, sits safely above the fair line, so it makes money. The second bet, win chance 49.1%, drops below the fair line, so it loses money. The two numbers differ by less than 3 percentage points, almost invisible to the eye, but one is above the line and one is below, and the outcomes are worlds apart. That's Demir's tragedy. His intuition was sharp enough to feel about the same, but couldn't feel those crucial 2 or 3 percentage points. And in a casino, it's exactly those 2 or 3 points that decide whether you're the house or the prey. You might ask, only 2 or 3 points apart, how does that lead to total ruin? The key is that a gambler doesn't bet once, he bets thousands and thousands of times. Any single round comes down to luck, bouncing up and down with no certainty. But bet enough times and that tiny disadvantage, like water wearing away stone, grinds your capital down bit by bit. The first bet, win chance over half, trends upward in the long run. The more you play, the richer. The second bet, win chance under half, trends downward. The more you play, the poorer. This phenomenon, that as the number of trials grows, the outcome converges toward the true probability, is actually the seat of the single most important rule in all of probability theory. We'll cover it in episode 5. It's called the law of large numbers, and it's the mathematical trump card that lets casinos always win. Let's wrap up this episode. When Demir wrote to Pascal about this self-contradictory arithmetic, to him it was just a little gambling annoyance. But Pascal realized there was a whole new class of problems hiding behind it that no one had studied systematically: how to use mathematics to calculate uncertain things. Remember 3 things from this episode. First, to find a probability, count all the possibilities clearly. Second, when you hit at least, use 1 minus the opposite. Third, never trust that scale at proportionally linear intuition, probabilities multiply. Next episode, we'll follow those letters between Pascal and Fermat and watch how they turned the question a game is interrupted partway. How do you split the pot fairly into the core concept of probability theory, expectation? That's everything for episode 1 of Probability, a historical series.